Okay, we're talking about groups. It's my favorite. Groups. And I'll call it part one because I think that's how it's given in the detail note. So I think this is 1.3 something. Okay. I was laying in bed last night, I was thinking about this, how I was gonna motivate this definition to you. And I thought of something. So here's a very unassuming equation. X plus 1 is equal to 2. This is the real stuff. This is why you're paying tuition, right? So assuming that the solution exists in the real numbers, right? What do we do when we solve this equation?
We add -1.
Yeah, we add -1 to both sides. So we're taught that we add -1 to both sides. Okay, so we add -1 to both sides. And what do we do then after that?
Do the operation.
Well, what do you mean do the operation?
Do the plus minus whatever.
So are you asking me to combine these?
Simple. Yeah, simple.
But this is in parentheses, so we have to do this
Yeah,
first.
we
Doesn't
don't follow
matter.
parentheses.
Doesn't matter the order that I add these.
So it's a property. Like,
Ah.
rearrange, and then we can use
So yeah,
an identity element, which is 0 with addition.
addition is associative, so we are allowed to say an x plus 1 plus this is the same as x plus and then 1 plus minus 1.
Wow.
And then this is 1, right? Now, that's by associativity. Now what? We
Combine
use
it
the
to
associative
0.
property and we combine to 0. Now, recall that we actually chose this element. Subconsciously, we've been trained to get always back to 0, right? Because we're trying to isolate X, this concept of isolating through an identity. So essentially what we're saying is in some respects, we chose an element that would cancel, and that is we have this notion of inverse. Right? Okay, so how do we finish? What's X plus 0?
Yes.
So
0 is an identity element on addition.
identity. You cannot solve a linear equation without associativity, inverses, and identity. So why are we solving this? Well, it's because we need to motivate a definition of a group. And so it's more clear kind of a relationship of what these things are. So here's the definition. So a group and we'll denote this with some binary structure. We'll call this G and then some binary operator structure. G is the set as the operation. A group G star is a set G together with binary operation star such that the following 3 group axioms are satisfied. And we actually already talked about what those set theirs are. We listed it out. We'll list it out in generality, basically. So here is the group axiom 1, and it's going to be of associativity. Right? So the way we're going to represent this is basically saying that I want A star B star C to equal A star and then B star C. I need that to be true for all A, B, C in G. And then second group axiom is actually identity is next, and versus is the third axiom. But so identity, the way we're going to make this statement is we're saying there needs to exist an element that we call the identity, and the identity is going to have a specific property. So there is going to exist, there exists an element E in the set G. Other textbooks, once they develop group theory a little bit more, they start using the digit 1 to represent essentially this notion of E. And it does not always mean it's literally the number 1. In the same sense, E is not the natural number here. And now the abstract sense, if we're talking about an identity, E is being used as fulfilling the role, for example, of 0 in this case. Okay, so there exists an identity element E in D, such that, and I use this guy. So it's a backwards in symbol to represent such that. There are different kinds of such that's. There is such that, such that, such that, stuff like that. I use this one in so like defining a map, defining parameterizations. Sometimes in set builder notation, this is definitely a set builder notation thing. So like a property inside of a set, inline in text such that. So it's like this is an inline statement, so I don't have to interrupt it with words. And then sometimes in a proof, you don't want to have all symbols, and so you can anchor yourself. Okay. This is a side note. That's that. What's the property of identity? Well, fundamentally, we understand that it's the element that doesn't change whatever you interact it with, right? So, you could say E star, because now we have a general binary operation, E star X will give you the same exact thing. It doesn't matter if you do E star X or X star E, because not all operations are commutative, so we account for both. And this needs to always return what? Yeah, X. And how many of the elements X does this need to be true for?
Everyone.
Every single one. So for all X in G. So this property can't hold for only half of the elements, because then it's not actually an identity on the entire group. And then the third axiom here is going to be, now we return to this idea of inverse. And what did the inverses do? Well, the inverse was that specific buddy element that was conveniently chosen to what?
Negate.
Yeah, and negating in addition, in this sense, is helping us get to 0. Subconsciously, we know that the whole concept of isolating a variable or canceling out to what? 0. It's the implicit element that's always in there, that we don't always say its name. And so what's happening is inverses is elements relating themselves to the identity, right? Oh, how do you get back to the identity within your overall set of things? So in the real numbers, if I had the number X, how am I getting back to 0? Minus X. So there's always going, essentially, we're saying there exists some sort of an element that acts as an inverse. What does it mean to be inverse? Well, if I interact this element with another, it will always be the identity. So abstractly speaking, I need this to be true for all elements A in my group. So this has to be true, and with the way we set it up is we first pick an element. So for example, like 1, that was the element that we picked here. So 1 would be kind of like A here. For all A in G, and that's just a comma, there needs to exist what? Basically, the element you can choose that gets us to the identity. So some A prime, not to be confused with anything calculus, it's just a symbol, right? So some A prime, sometimes they'll call this A inverse. The only reason I don't use A inverse is because it keeps you too attached to things you already know. And the idea of abstract algebra is you're abstracting ideas. So A prime, now does the inverse, would it make sense if I put like a matrix in here to solve an equation with real numbers?
No.
Right, that'd be like, what on earth are you doing? Matrices aren't even in this set of real numbers, and so. The inverse, this is very important. It has to actually be also in the set. You can't just have a random inverse and picking it from somewhere. This inverse needs to also be a member of the same exact set as the element it can. And then the property for inverses that cancel the identity. So for all A and G, there exists an inverse element A prime also in a group such that, and then your property. It's actually very similar to this identity thing, where A interacting with its inverse should give the same thing as the inverse interacting with the element. What do we expect that to be?
E.
E, yeah, the identity. So, let's see, for all A and G, exists A prime. Cool. So that's a group. We have a binary structure. We basically take the set, we close it under some sort of operation, and we observe, okay, we need associativity. We need there to exist this special element we call an identity. And it needs to be in this the specific element that always returns whatever object you had, element you had, number you had, matrix you had. And then the inverses is the way that you get back to the identity within the same set. So how are we feeling about this definition?
It's taking a while to decrypt it, so used to having.
What I'll do is I'll keep it up here then, and then I'll do examples over here to give a little bit more concretized, ideas. So let's take a look at, let's pick a set. Let's do, I guess, real numbers, keep it easier. First, let's do regular multiplication. So is regular multiplication associative? Yeah, right. So basically we have that A, B, C is equal to A, B, C, and that will be true for any real numbers that you choose, right? And so some associativity. And then, well, what's next? What do we need to show for this to be a group?
Identity element.
Yeah, we need an identity. Okay, so if you're multiplying real numbers together, what is the one element in the set that is always going to return back to you the element that you interact with, multiply with, right?
One.
So we can say that there exists the element 1. That is a real number. Such that if I take x and I multiply it with 1, that's the same exact thing as I get if I take 1 and I multiply it by x. And specifically, what is that giving me? Well, x. That's the whole point of this, right? There is some element that's just returning back to me x. That's always going to be true, so long as x is a real number. This is identity. Okay, are we done?
Inverse.
Right, we need an inverse. Okay, so we need to first select something. So what we're going to do is I'm going to select so a real number A. Now, there exists what element also in a real number set that's going to fulfill this property?
1 over A.
Yeah. So 1 over A, is 1 over A real?
Yeah. Since A is a real number.
But here's the issue though. If A is allowed to be real, here's the question I gotta ask. is this always true?
Well, if A is 0, it's not true.
Well, you tell me, is 0 a possible real number choice?
Yeah.
Mhm.
Hmm.
But 1 divided by 0 is undefined.
So,
So you just say, set that A is not equal to 0?
but the set is including 0. So you see, it only takes one bad apple to mess the entire thing up. This fails to exist. Because A could be 0. So when you make statements in mathematics, you are making an always statement. And that's way, if I like, so you might say, well, but 0 is just a special case. And what if you just multiply 0 by 0 and then it's fine? Well, that's not how identity works. You can't have multiple inverses. You can't have multiple identities. So we could either say that would not always be in R, or you could say there does not exist, whatever, but only can do it this way. And so essentially, we have this issue. If A equals 0, 1 over A, and basically does not exist, it's undefined. And another way we could say this is 0 in R does not have an inverse in R. So we have a real number that doesn't have a real inverse.
Bless you.
Now, what about every other value of A?
It should work.
Yeah, it should work. And so we have a way to actually patch this little fix in math. So what we do, instead of taking all of the R for a multiplication, to counteract this issue, we do R0 removed. R0 removed. And the way we notate a set where you remove 0 is you superscript a little asterisk, not to be confused with a binary operation. This is the set reals without the element 0, and it's really nice because this allows us to do division. Because can you divide by 0? No. So this R, so the whole set R times, is that a group? Oh, not.
So what would it be considered instead?
Well, there are several subcategories of structures for the group axioms. I actually don't remember all of the names, but it's definitely in the textbook.
Okay.
But for now, we can basically say, all right, it doesn't work, it's not a group. Now, if I took this corrected set, R star, with regular multiplication, is that a group? Yeah, because then now we actually can have that inverse, where the A times 1 over A is always going to give you back the identity Y. And you don't worry about division by 0. Okay. Are there any questions about that example?
Would you say the R star stood for again?
It's defined to be a very specific set of numbers where you just take whatever this set is and then you remove the element 0. And further, if you take some subset A, a subset of R, then a star is then A without 0. So what this means is if I take the set of integers and then add that little asterisk there, that's saying, well, I want all the non-zero integers.
Do groups have to be onto whatever set they're working with?
Well, my question to you is, what is the definition of onto?
So there's a mapping that exists perfectly like to another one.
So does it make sense to have something, an isolated set being onto? See, but this is good. This is good. So it brings up a great. This is how you learn mathematics at this point. Definitions are basically going to be the only source of mercy you have in the entire class, because nothing's going to change. The definitions will never change until some smart person later on says, we've all been wrong this entire time, and then they change that. But when you're doing an exercise and you're reading the words in the question and it's just gobbledygook, it's going over your head, right? Or you read a theorem and it asks you to prove it, and you're thinking, I'm not Jesus himself. Like, how am I supposed to solve, right? Always return to the definitions. I think the power of being able to relate properties and definitions, qualities of definitions, what definitions entail, what definitions just say about themselves, is 90% of proof writing. So if you're trying to do a theorem where it's talking about, say, maps, or is this an isomorphism, or blah, blah, blah. I mean, the first question you should simply ask yourself is, what are all of the individual math terms in here? Because if you can't identify what you're even talking about, then yes, it will be really hard. You won't know what's going on. And so always anchor yourself. That's my biggest tip. That's what I found to be the most helpful, is when I'm doing, especially some of the homework problems are just hard. Objectively, they're difficult. And when you tackle something you don't know how to do, or Dr. Lang, he doesn't have time to cover everything in class, right? Because he's just presenting you what? The definitions. Why is that the most important thing? Because if you have the definitions and you internalize them, that's all you technically need to basically get from an exercise that you haven't seen before to some sort of improvement. So don't forget about definitions. Any questions about that? It's a different way to think about mathematics. It's a little different than having formulas that you kind of work with, or procedures you work with. Yeah.
So with this, what we just did here, would that be like the format of how we should answer every single problem in this class, like to get used to doing what you just did?
Here's what I'd say. This is what you're going to want to memorize, because this is almost on every single time Dr. Lang does this class. He asks an exam question that's just the definition of a group, because it's that fundamental to this class. So what I would do is I'd memorize this. I'd memorize the axioms, just by rote. And then when you're given the opportunity to practice in exercises, emulate the properties, emulate the notation, emulate the way of reasoning. Say it out loud as you're doing it, because then it's not just going to be a bunch of simple soup. This will actually communicate some sort of direct logical reasoning. So in the same way that I don't just memorize, oh, I need to make sure it looks like this. I'm communicating the argument I'm trying to make to you, and then it just so happens to use symbols instead of words. So that's what it should feel like. Yeah.
Okay, I see what you're saying.
So it doesn't need to follow a formula. See, that's the liberating part of this class, is now you have permission to think for yourself. And it's this really great thing where you're no longer really restricted to following a set list of steps and procedures and stuff like that. If you know what the definitions are, you can adhere to them, you can communicate with them, and then just practice representing that argument with symbolic notation as you go. Make sense?
One last question.
Yep.
What would you recommend as the best way to memorize and learn, like internalize all these definitions? Is it just a practice, or would it just be like thing, like,
Okay, yeah.
like read them over and over again, or like flashcards, like what would you recommend?
It depends on everybody. Some people can just look at stuff and memorize it, and that's very aggravating, because then it seems like a hack. But for me, I have the memory of like a potato, so I handwrite my definitions a lot. The more times you write this out and talk yourself through it, the better. And then also when you're doing exercises, you're reiterating the same concept over and over and over and over and over again. And so that repetition of having to know the definition for 8 exercises in a homework set, it starts to get it in your system. So best thing to do for memory, just do the homework. And then as you're doing the homework, appeal to the definitions so that you're forced to rewrite it and forced to see it over and over and over again. And then use each of these properties, for example, over and over and over again. And so that kind of thing comes with time. So you can microwave a Hot Pocket, but you can't microwave Thanksgiving turkey. And this is Thanksgiving turkey. Yeah. All the other courses, kind of like DiffyQ, Calc 1, Calc 2, those are kind of microwavable. You can kind of just memorize the formula sheet, and you can kind of get through it. But that doesn't really work anymore because it's abstract. And so if we're talking about the abstractions, then differences in example isn't really the main point now. It's differences in structure and differences in property. And the only way you can inherently practice that is if you just force yourself to solve new problems you've never seen before. So, okay, let's talk about cancellation laws. Cancellation. Oh, since you're getting extension on the homework, I thought I received a lot of emails and there's a very common pattern happening. If you're proving something to be not something, that's when example suffices. But if you're trying to prove that something satisfies a definition, that has to be now true for all. So if you're trying to show that a binary operation, say, is associative, right? Well, if you find an example where it breaks down, that actually constitutes as a valid proof. Why? Because you broke it, like you found a way to break it and it doesn't work. But if you're trying to then say that it is associative, single example isn't cutting it anymore. For the same reason that, like in the previous thing we just did, you can miss loopholes in the system, right? So if you find something is not like associative or not commutative, yeah, a numerical example that demonstrates that it breaks is fine. But I don't want to see just a valid example being used in substitution for an actual proof of the general property at large, because then you've actually proved nothing. If your goal is to show that something is associative, but you only say one example, you just found an example. And that no longer is true for all of the things. And then inherently, and it actually defies the definition of associativity, because what we always forget about is the little tiny tidbits at the beginnings and the ends of definitions. And the tidbit at the end is for all, A, B, and C, and X. So make sure you'll know when a proof is done if you're proving it to be something, because you'll be able to go back to the definition and be like, yes, I have shown that whatever I was trying to do satisfies all of the listed properties that constitute this definition. So it becomes definitionally accurate. Okay. Cancellation. This happens when you take elements and, well, you use inverses and take advantage of associativity like we did in the beginning. So if I take A star B, and if I have this equal to A star C, then if these are in a group, then, well, yeah, okay, let me be more specific. So let's push this back. Let's define a group. Let's just choose something. Let G star be a group with A, B, C, and G. Okay, so we've chosen some elements that we make sure are in the set. Now, the cancellation law is essentially saying that if I take A star B equals A star C, this implies what? What do you think? Yeah, B or C. I mean, if you take the same thing, we're essentially canceling the same stuff. Is that the only direction cancellation goes? Well, if I do something like A star B is equal to C star B. Okay, what am I canceling now? Canceling the B's and so on. Now, here's what I don't want you to do. I don't want you to get attached to the specific symbols of the specific variable choices I make. If I just put if I put a smiley face here and a square here, and then like a picture of your cat here, the properties are still the same because it's about structure, not about specific symbols. Okay. So in the textbook, if you are taking notes and you're reading the book, and it doesn't say, instead of doing A star B and A star C like that, and when it doesn't do A star B and C star B, it might do B star A. and C star A, right? Is that different? No, why? It was because it's about structure, it's about the property overall. So don't get attached in that sense, because then you'll be attaching abstraction to things that aren't even abstract. And then it's confusing. Okay, so we can actually prove that this works, given our group axioms. So let's start with what we call in proofwriting. I know that how many of you have taken a rigorous proofwriting course before?
What would constitute a rigorous, like discrete math?
No.
Or is that not rigorous?
No.
Then no.
Okay, so here is how proof works. The first part of a proof is always what we call the preamble or the hypothesis. That is essentially you're laying the groundwork for what to do. I liken proofwriting to cooking a meal. You can't cook without ingredients. And so what happens is people just try to dive in and they don't have any of their ingredients on the counter. So if you're going to create a lasagna, but you don't have tomato sauce and pasta for the lasagna, well, yeah, it'll be confusing when you get halfway through and you can't actually finish, right? So get your ingredients, the preamble. We need this, okay? So I need a group. And I need some stuff in it, right? I need to be able to talk about some elements in the group. Now, I know I just copy and pasted this. That means it's probably right. Because we're not proving anything yet. We're just gathering together the ingredients. You haven't started cooking, but you can't cook if you don't have any food. Okay? Now, what's the condition? What are we at? What is the goal? And I'm going to introduce this little abbreviation. We want to show that A star B equals A star C implies B is equal to C. That's the goal. Obviously, there's this one, but the way that the logical structure of the proof is essentially identical, so I'll leave that as exercise to you. In exchange, I'll make sure you really understand how this proof works, right? Because again, it's about structure, it's about properties, it's not about specific details and specific symbols. So, well, if that's what we're trying to show, and in logic, basically, this is the statement P, this is the statement Q. So we need to start with P, and then eventually end up with statement Q. So we're going to let, or suppose, either word is fine here. This word is going to be your favorite after the end of this class, so is this one. A star B is equal to A star C. Why am I allowed to just assume that?
Because of the axiom.
Yeah, well, because it's the premise of the entire thing I'm trying to prove, right? So if I'm trying to prove that this gets me here, then it's okay if I start here. I've been given through the cancellation law, essentially permission to assume that in my hypothesis. And now from here, obviously I can't just finish the proof by saying, and that implies B equals C, right? I now have to fill in the work of how we get down the roadmap and then end at this conclusion. So let's see what this actually implies. If A star B is equal to A star C, and we are talking about a group, are A, B, and C elements of this group? Yeah or nay? Well, yeah, because it's in the hypothesis. We literally put them in the group. Okay, so that means every single one of these properties they have to satisfy. And we take advantage of that. So ultimately, the goal is this. We're trying to get rid of BAs. I mean, when you look at this visually, that's kind of the concept, to cancel what's the same on both sides. And the way we can do this is we can multiply, and I use multiply not in the sense of actual multiplication, it's just the word for general binary operation, is we can multiply by plus. Well, remember the inverse. So I have A inverse and this is where you need to be careful with notation. If A star B, A inverse star A star C. Notice that I keep these in parentheses. Because that still is just a singular element. And so we're treating this as a singular element because that's kind of what it is. It's just the element A star B is guaranteed to be inside of the group because the group is closed under its binary operation. Okay, now. What are we allowed to do now? It's associative. So because this is a group, then it must satisfy the associative property. So I can have A prime star A star B, and then I can have A prime star A star C. And the reason I can say that is because this is a group. This is axiom 1. That makes sense. We're allowed to do this because associativity inherently is definitional for groups. We're playing with a group. That's our preamble. Those are that's our hypothesis. So we're allowed to use and take advantage all of the properties that come with being group.
So it's not enough that we can just write the step before that, where we're multiplying by the inverse. We can't just skip ahead and just do, that would mean B equals C.
Right, because I mean, if we're skipping ahead, we might as well just not prove anything because we know what it's supposed to be. So the concept of a proof isn't the answer, actually. Concept of proof is, why can we know that this is actually how we have the answer? And so the roadmap, in this case, the roadmap is going to be more important than just knowing what that last line is going to be. That's what lower level classes are for. That's what your 200 level math class is for. Memorizing theorem, oh, here's the conditions. Okay, then that. You don't prove it, you just accept it because it's true. Now we're stepping back and saying, okay, great. Math isn't just the substance of how many theorems I can memorize. It's the substance of how many theorems I can prove on my own. And can I understand the logical math to get to these results? Okay, so here's this associativity. What's next?
Inverse?
Identity.
No, identity.
Identity. Well, why are we talking about identity?
Element operator known by its inverse will give you the identity
How do you know that?
because it's G3 and G2.
So essentially you're citing definition. You see how every single thing in proof cites a definition of some sort. So this is the element E in the group. Because that's the property definitionally for inverses. Inverses. And technically, to do this first step at all, you're citing the existence of an inverse too. You can only cite the existence of an inverse if you're in a group. Otherwise, that inverse is not actually guaranteed to exist for you. So we are technically using inverses up here as well. Okay, what's next?
Just say B is equal to C.
Yeah, why?
Well,
If this truly is a group, the identity times some element in the group is definitionally always going to return one.
So
Itself.
what does the E mean again?
Identity. So it's satisfying. So think of like 0 with addition. If I take the number 5 and add 0, what do I return? Yeah, or like 10 plus 0, or A plus 0, X plus 0. Always returns the same exact thing with addition. Here, we don't have addition, we have a general binary operation. But the idea is, okay, here's the identity that corresponds to that, so it'll return itself. E star C, well, it's the identity, so it'll just return C.
Oh, okay.
This is identity. Well, I mean, isn't that the whole goal of what we're trying to show? So we have a roadmap that's completely tied through the group axioms that gets us from this equation A star B equals A star C, and that logically applies B is equal to C. Do you see how this is reminiscent to the little x plus 1 equals 2 equation we did at the beginning? And also, do you see a roadmap? So given this, do you see a roadmap for how you would do the other way around, right? So if you're trying to cancel now the stuff on the right,
Yeah,
because you roadmap what? Well, B is what we're trying to get rid of, and because B is in the group, there's going to exist an inverse for it. And so we'll just put the multiply on the right for that inverse, and then it'll be associative. The inverses will cancel to the identity. And done. Okay, so this is all the hardware that goes on when you do your basic linear equations. It's pretty cool. We take a lot for granted. All right. You guys get out at 8:30, right?
9:35.
9:35.
9:35. Okay, do you want to see linear equations?
Sure.
Okay. And then on Monday, I'll let Dr. Ling know to pick up on uniqueness of identity and uniqueness of inverses. So basically, -1 is the only inverse for the element 1 with addition in the reals, right? There's not going to be some other element that is the inverse to that element. Now, it is possible for an element to be its own inverse, right? So in binary, wait, raise your hand, you're computer science, any other computer science people? Cool, right, so if you're counting in binary, you got two elements, you got two drops, it's 0 or it's 1. And then one switches you back to 0. So that means 1 its own inverse, right? Because it returns itself to the identity. In the same sense that 0 obviously is definitionally its own inverse because it will get itself back to the identity or itself. So that's okay for that to happen. If you end up in an example or an exercise where one of the elements ends up actually being its own inverse, that sometimes happens. And so long as it's used up only once in the group. Okay, linear equations. I like to joke that we climb the ladder of math classes and we get to the 400 level math class just to relearn how to solve a linear equation. And it's like, whoa, we made it. I can solve a linear equation. No, I almost lost my mind yesterday. I basically I was doing topology, and you spent exorbitant amount of effort to prove something ridiculous like connected, not connected. But you would think it's not as difficult as it ends up being. Okay, so if I want to solve a linear equation, so for example, in general speaking, so we need to be in a group, otherwise we don't really have anything to talk about. So again, I'm giving myself ingredients. I'm telling you exactly what I'm interacting with, so there is no ambiguity. That's always the key. This be a group, so be a group. Your textbook will start just using the letter G by itself without the full notation. That's okay. They're implying all of this stuff though. So if they just give you the letter G, just assume that star is going to be that general operation, unless it's explicitly stated. And then I'm going to need some elements. Let's see what elements I need to do if I want to solve this equation. So let's do something like x star A equal to B. So I'm going to choose some x, A, and B in my group, right? Semicolons are powerful commas. Basically, you can separate stuff out that has punctuation in it. Okay, so we're saying that this linear equation is guaranteed to have a unique solution in this group. So the equation has a unique solution in G. What's this really saying? Well, if you have the equation of a line and you're solving a linear equation, are you expecting to have 2 roots? Are you expecting to have 5 solutions to your linear equation? I really hope not, right? So That's where some of that stuff comes in from high school level algebra. We can make those relationships. So here, what we're gonna do is we're gonna first show that there is even a solution in the first place, right? So, well, what do we always start off a proof with?
Oh, yeah, that.
Specifically,
Hypothesis.
the hypothesis, right? What ingredients do we even need to get this going? Well, that. So, even though it's a little bit redundant, I'm going to do this for the sake of example for you. Be group. And I'm gonna choose elements X, A, and B in the group. So now, every single time I refer to X, A, or B in this entire proof, you know exactly what that is. They're members of a group. Which one? G, okay? And now I'm going to suppose that we have the equation X star A equals B. Did he talk to you about the definition of equals yet? Okay. So you'll know what that actually means, that this element relates to this equivalently. Alright, what are we trying to show? Like when I say I want to show, do I know what I want to show?
Yeah.
What do I want to show?
X star A equals B.
That's a unique solution.
Well, I want to show how exactly it has a unique solution, so the equation has a unique solution. In G. Cool. I have my ingredients, I have my goal. Now we go for it. Right, so we take X star A equals B and see what we can get out of this. All right, we're in a group. We're trying to isolate X. So what should we do?
Take the inverse of A.
Yeah, we know that. Why do we know that there is an inverse of A?
Because A is real.
Because A is in group. Oh yeah, right, okay. So X star A prime, the inverse, will be the same as B star A prime. So that is existence of an inverse. And then associative property lets us actually perform the cancellation, right? So associativity guarantees that I can do it in this order. And then X star E, because by definition, an element with its own inverse will give you the identity. And then X star E definitionally returns X if E is the identity. So B star A prime is B in G.
Yes.
Is A prime in G. Okay, so if I have a binary structure like this, is G closed under star?
Yes.
Definitionally, B star A prime therefore must be in G. X therefore is G. And it's a solution. So B star A prime is the solution to the linear equation X star A equals B. Now, I don't have time to do the unique side, but I'll tell you how you logically do that proof. The proof simply consists of this argument. Oh, I should put closure here. It says, okay, well, to prove that something's unique, we're just gonna say it's not unique. And then we're gonna say we have two different solutions to this equation. And what you're gonna do is when you actually put them together, you can use and cite the cancellation law that we just proved to essentially say, well, it just cancels, and you end up that with this fact that both solutions end up being forced to be equal to each other. So if two distinct solutions are logically forced to be equivalent, that means there is no two different solutions, it's just that one solution. And that makes it unique. So that strategy is used a lot. I know that Dr. Ling will talk to you about that, especially for identity, and that inverse. Okay, so any questions about this before dismiss?
For the unique one, would we just switch out the variable for b then? And do another set of problems to show that it's unique?
What I would actually do is I'd say, okay, let's let x and x prime be distinct solutions. Now, ultimately, I'm going to show that they're that possible. But by assuming that they're distinct solutions and forcing them to go up into the same equation, it's going to result in cancellation that says, whoops, x and x prime are actually the same exact thing. It's unavoidable. So then that's why it's, yeah. It's also that's outlined in the textbook pretty clearly if you want to see it. Cool. If there are no other questions, free to go. Homework is, I guess, been extended to Friday. So all the stuff that goes up until 1 point, whatever he finishes next this week, and then that'll be due Friday.
So what's the difference